Hi, I am Hoyoung Choi, and I'm a researcher at Hanyang University in South Korea. In this video, I'll present our paper, Adversarial Normalization, I Can Visualize Everything Ice. This work is done with Seungwan Jin and Dr. Kyungsik Han. In this paper, we propose ICE, a novel method that enables a model to directly predict a class for each patch in an image. ICE distinguishes background from foreground regions by predicting background classes for patches that do not determine image classes. ISA performs other existing explainability visualization methods on the image in a segmentation dataset and achieves comparable performance to the state-of-the-art methods on the CUP and the VOC datasets. By incorporating ICE to the encoder of the EITS, ICE demonstrates its performance on the accuracy and efficiency comparable to EVIT. From now on, I'll explain more about our work. To explain why the model predicts what they predict, we need a transparent visualization method to understand why the model made such predictions. The primary focus of previous studies was to utilize attention scores between CLS tokens and other patches to discriminate patches that strongly influence the learning process and enhance the interpretability of vision transformers. However, this approach resulted in a partial emphasis on the foreground region, thereby failing to adequately highlight the entire foreground area. We note that the output embedding vectors for each input patch token in a vision transformer retain the image information of each patch location. Our assumption was that these vectors can help predict the foreground region separating background. While many methods have been proposed to effectively visualize explainability, previous studies encountered challenges that hindered the comprehensive highlighting of all foreground regions. These challenges pertain to structural characteristics of vision transformers. The contributions of our work can be summarized as follows. We propose ICE based on the notion of patchwise classification and adversarial normalization. ICE significantly improves foreground and background separation over original DITS, achieving comparable or superior performance than existing self-supervised learning methods. We demonstrate that ICE is effective in background patch selection, showing comparable efficiency and accuracy to EVIT. This is the overview of ICE. We propose the fine-tuning process of ICE, which enables a model to directly predict a class for each patch in an image and a loss function for adversarial normalization. We propose adversarial normalization, which distinguishes all patches between a class and a background. It normalizes prediction probability of each patch token and makes all patches have prediction results. We intend to have all patches continuously receive gradients of background label during training so that all patches have probability of being background. We reflect a background probability of all patch tokens adversarially by normalizing the prediction probability of each patch token. We separate background patches by comparing the probability of background and a class of each patch token. Adversarial normalization consists of two phases, background phase and class phase. For the background phase, we get one vector using the average of all patch tokens and multiply scale alpha to maintain a degree of loss. A background label is a one-hot encoded vector with only the last class as a true value. We can get a background loss by calculating a cross-entropy loss between B head and a background label. For the class phase, we construct decision mask D head IO patch that predicted the background the highest becomes 0, otherwise 1. We get one vector using the average of remaining patch tokens, which are class-related patches. We can get a final loss L total by adding L class and L background with the class weight lambda class. Here are the qualitative analyses of multi-class image segmentation. For the class-specific visualization of two different class objects in the image, ICE shows class-specific characteristics by directly predicting classes of foreground and background regions. For the single-class multi-object image, ICE adequately distinguishes foreground and background regions, highlighting the area of the object in the image. Here are quantitative comparisons of segmentation performance on the image in a segmentation dataset. ICE outperformed all explainability visualization methods, and ICE-F showed comparable segmentation performance to robust VIT. Note that ICEP is a method that freezes the parameters of DITS and trains only two LP layers. For the segmentation maps on VOC dataset, compared to the visualization by applying raw attention to the original DITS, I significantly improved the performance of semantic map segmentation by separating background and foreground regions. Furthermore, we found a tendency that our method distinguishes the background relatively well compared to the self-supervised learning methods. I achieved superior Jaccard similarity performance on the VOC dataset. In addition, other methods except ICE show performance that tends to vary with key hyperparameters. We conducted weekly supervised and unsupervised single-object discovery experiments on the CUP and the VOC datasets. As a result, ICE outperforms other methods in the ground truth localization and achieves comparable performance in the top first localization on CUP dataset. Also achieved comparable performance compared to the state-of-the-art methods on VOC dataset. To examine another aspect of effectiveness of background patch selection by ICE, we evaluate the accuracy and efficiency with DIT and EVIT. By applying ICE to DIT encoder, the throughput performance significantly improved while maintaining comparable accuracy. This result indicates that the patch selection of ICE may help improve classification performance than EVIT. In addition, we conducted an evaluation study to test the influence of background scale alpha and class weight lambda. We found a significant drop in overall performance without the background scale and class weight, highlighting the importance of these two parameters for effective learning of ICE. This is the end of the presentation. Thank you very much for listening.